1920, Georges Lemaitre was ordained a priest. He was an exceptionally talented man who, while studying theology, was able to teach himself relativity. From 1925, he was professor of physics at the University of Leuven, a post he held for the remainder of his life. It was at Leuven that Lemaitre studied the expansion of the universe. He realized that in the past it must have been more densely packed together, so he postulated an explosive beginning. We should see our world, Lemaitre said, like a display of fireworks just ended, some few red wisps, ashes, and smoke. Standing on a well-cooled cinder, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origin of the worlds. For centuries, astronomers had worked out fairly detailed models for the origin of the solar system. But Lemaitre was interested in something far deeper, the origin of the whole universe and of all of the atoms that make up everything around us. Now, there are two ways that one can build new kinds of atoms. One is by the nuclear fusion of light elements into heavy ones. Lemaitre was aware that in the centers of the sun and stars, where temperatures get up in the millions of degrees, nuclei of hydrogen combine to make nuclei of helium, in the process giving off the energy by which stars shine. But with the conditions that were calculated for the centers of stars, and with what was known about nuclear physics, Lemaitre thought it was impossible that one could build the heavy elements, such as the kinds that make up the world. So he looked to the other possibility, namely fission of heavy elements into light ones, or, for example, the radioactive decay of uranium through radium and into lead, with the consequent emission of all kinds of various radiations. Lemaitre had the idea that the atoms of the universe came from one huge entity that he called the primeval atom. And in some kind of primeval blast, this atom disintegrated into myriads of parts, and each of them further broke up until the inconceivable number of atoms that make up the universe resulted, with their present abundances. But then what about the radiation given off in the process of the radioactive disintegration? Well, about that time, physicists were learning about cosmic rays, these subatomic particles that hit the Earth from all directions. And Lemaitre identified the cosmic rays as the radiation given off with the disintegration of his primeval atom. Lemaitre could only speculate in those early days. He wrote of his primeval atom, "It will have to be modified, perhaps, when our knowledge of atomic nuclei is more perfect." His idea that the universe had an explosive beginning and that it has been evolving ever since obviously posed deep questions. Research here at Pasadena, California has answered these questions. At the Kellogg Radiation Laboratory of the California Institute of Technology, physicists have produced theories of nuclear astrophysics of the early universe and also done experiments to check them. Creating the universe in the laboratory would have seemed strange to Lemaitre. How are these new ideas different? Alan Cooper.
The contribution made by Lemaitre was to set everybody thinking about the early universe by asking the right questions. Was it fission or fusion reactions which produced the nuclei? Were the cosmic rays made of the same nuclei that we see all around us? It was George Gamow who made the next step. He worked out that the early universe must have been extremely hot, much higher temperatures than in the stars. And at those temperatures, you can't possibly have this single vast nucleus which Lemaitre had talked about. In fact, on the contrary, in the very early universe, at the very beginning, there can only have been the simplest elementary particles, protons, neutrons, electrons, and so on. And around 1948, Gamow made the concrete suggestion that in the early universe there were fusion reactions between those elementary particles at a temperature of around 1,000 million degrees. But to go further with his theory needs hard facts. This is a machine which was designed to produce those hard facts. Above me, in a big steel cylinder, is an early type of high-voltage generator, a Van de Graaff generator. And the voltage of that accelerates protons and other light nuclei down this tube in a beam. We can see that there is a beam. If I put a quartz plate, you see the blue spot where the beam passes through it. And then the particles come down to a magnet, and the magnet selects the speed of the particles, and the speed can be chosen to correspond to the temperatures involved, 1,000 million degrees. And then the particles, having been bent around, move along horizontally towards a target chamber. This is the target chamber, which we've opened up now so that you can see it. This would normally be inside here. Now, the accelerated particle in this position would come along and can strike the target here, and it'll collide with a nucleus in that target. Maybe it'll just be deflected, but very likely it'll be transformed by that collision into some other nuclei. And those nuclei can be detected here, identified, their energy measured, and all that recorded. Then, tiny fraction of a second later, another particle comes along. All that is identified and recorded, and so on, and so on. It's a very long job. In fact, it's no less than recreating the early moments of the universe, reaction by reaction. That's what's involved in turning speculation into a firm prediction. Some of the reactions taking place in this target plate are identical to those in the early universe in the hot Big Bang. In the Big Bang, protons and neutrons moved fast in the high temperatures. Sometimes they just glanced off each other, but sometimes a collision resulted in this, a deuterium nucleus. There's excess energy from the collision, which is emitted in the form of a gamma ray, leaving a stable nucleus. A deuteron can then collide with another proton and form helium-3. Collisions between two helium-3 nuclei also occur and form helium-4 with 2 protons to spare. Many other reactions take place, but the end result is a simple mixture of light nuclei created out of the original pool of protons and neutrons. Helium at mass 4 can't absorb a proton or neutron and turn into something of mass 5 because there is no stable nucleus of mass 5. So in the few minutes before the universe cools down and stops the reactions, they don't get beyond helium. So if helium is the dead end, where do all the heavy nuclei come from? Well, we have to think about the stars again. Long after the Big Bang, when galaxies had condensed and individual stars had condensed, matter was reheated again in the centers of stars. Now, at first sight, it doesn't seem as though that helps very much, because the stars start from hydrogen and helium as well, so they should have the same problem with this gap at mass 5. But there's one very big difference. The density in the center of a star is very much higher than in the Big Bang. 2 physicists, Salpeter from Cornell and Hoyle from England, found a way to cook up the heavy nuclei in the centers of stars. Glancing collisions between helium-4 nuclei will be common, but sometimes they will stick together very briefly. Suppose that at the crucial instant, a third helium-4 nucleus strikes them. A gamma ray is released, leaving carbon-12, a stable nucleus, and for us the most important one in the universe, for carbon is the basis of life. So 3 helium nuclei can succeed in sticking together where 2 had failed. And it was a brilliant success by Hoyle to predict exactly the special properties which carbon nucleus has to have in order to allow that process to carry on. Prediction of the properties which were confirmed very precisely by a machine very similar to this one. And in fact, Hoyle went on with Burbage and Fowler at Caltech to work out a large section of the life history of a star. Late in its life, a star often explodes and sends out matter into space, and it's that matter which condenses into planets and which ends up in you and me. That's where the heavy nuclei come from. The point of all this is that it needs both processes, fusion in stars and fusion in the Big Bang, to give the right mixture of nuclei that we see all around us. And it's the success of this overall picture which is the vindication of Gamoff's idea of high temperature, of all the nuclear theory, all the calculations, all works together to give the right picture. A long, long story, but what a wonderful result. An understanding of the stars and a recreation of the first minutes of the universe. Having worked out all that story, it tells us much more. It tells us, for instance, that the radiation which must have been present at the Big Bang because it was so hot, that radiation must have survived until the present day. Gamoff realized that and suggested that a search should be made for that radiation. But perhaps not even Gamoff realized how important that was going to be. 30 years after his original paper, 2 American physicists shared the Nobel Prize for Physics. Arno Penzias and his colleague Robert Wilson discovered the radiation that Gamoff had predicted would come from the hot gas of the early universe, radiation that would still be present in the universe today. This accidental discovery ranks in significance with the expansion of the universe as one of the great cosmological discoveries of this century. There's a close analogy between the sun's radiation and Big Bang radiation. In both cases, they're produced originally in the form of X-rays and gamma rays by fusion reactions at very high temperatures. In the case of the sun, that's in the core of the sun, and then the radiation diffuses around, it's scattered around for about 1 million years. It takes 1 million years to reach the surface, and then the light gets free of the surface and, of course, can travel freely through space, and some small part of it reaches us. In the case of the Big Bang, the radiation is also diffused around, again, as it happens for about 1 million years, before a unique event happens. Atoms are formed, neutral atoms. Now, neutral gas is transparent. We can see through neutral gas. And so the light then becomes free and can travel towards us, a signal direct from the Big Bang. But how can we recognize that radiation? Well, in the case of sun, of course, it's quite obvious. We know where the sun is, and we can recognize the radiation by knowing where the radiation is coming from. In the case of the Big Bang, radiation fills the universe evenly, so it's not so much a matter of knowing where the direction of the Big Bang is, but the fact that the radiation comes equally from all directions. And that is a help in identifying the radiation, but it's not enough. Something else is needed. Well, radiation from a hot gas has a characteristic rise and fall of intensity with wavelength. And that's the clinching factor in recognizing the radiation. Both the sun's radiation and the Big Bang radiation has this same basic shape. But in the case of the Big Bang, there's an important extra factor. The radiation started to travel freely through space after 1 million years, but that's really a very short time, because that radiation has been traveling towards us for all the rest of the lifetime of the universe. Then that's or say 15,000 million years, which means in turn for 15,000 million light years. Well, light from big distances is redshifted like the light from the distant galaxies. So light which is coming from such a very big distance is very much redshifted. It's redshifted right down to the radio range. But happily, this characteristic shape is maintained through that redshift, so it can still be used to identify the radiation. The only effect of the redshift, if you like, is that because of it, the Big Bang looks like radiation from a cool body and not from a hot body.
Those radio waves should easily penetrate the cloudy skies of New Jersey on the east coast of the United States, where Princeton University physicist Robert Dicke, in the 1960s, thought again about Gamoff's earlier idea. He suggested that the theory should be looked over again, and his younger colleague, James Peebles, confirmed that with modern technology, we should be able to detect that background of radio radiation.
How can this radiation be detected, now that we know how to recognize it? Well, it's redshifted all the way down to radio wavelengths, so we need a radio receiver. This may not look much like a radio receiver, but it is. I don't think I look very much like a radio transmitter, but I can show you that I am. This is just a cover. If I put my hand underneath it, you can see that this apparatus very easily records the radiation coming from my hand. In fact, it's sensitive enough to record the radiation from the Big Bang, and it's been used for just that. Taken outside, this piece of apparatus must record a uniform radiation coming from all over the universe. And the first requirement is to get above the ground, so as to avoid the Earth's radiation at radio wavelengths. The group led by Professor Dicke did their initial experiment from the roof of the biology building at Princeton. This is the receiver that was built at Princeton in 1965. It could be tilted to check that any signal they got really did come equally from all directions. And the signal was collected in the main horn. It was led down and then across to a detector. And the signal was compared with that coming from a reference source at the bottom. And this apparatus is set to 3 centimeters wavelength. Because the Princeton physicists had worked out all the theory, they knew exactly what they were looking for. But they were not the first to see it. 25 miles away, at Homedale, still in New Jersey, are the Bell Telephone Laboratories.
The laboratory's delicate horn antenna was hardly designed for cosmology. Its main use is for satellite communication. But after all, it is a horn antenna, and it could be used for radio astronomy. And physicists Arno Penzias and Robert Wilson were doing just that. They were using this horn to make measurements of the radio radiation from various parts of our galaxy. But they encountered an unexpectedly high level of background radio noise that simply wouldn't go away. They spent nearly a year exploring everything that they could imagine that could account for this unexplained radiation. They were finally able to eliminate the galaxy as a source, and also the solar system and the sun, the air around the horn, and of course the ground beneath it. Well, perhaps the trouble lay in the instrument. Now, there were a couple of pigeons that made their home in the horn. They would snuggle into the throat up near the observing cab where it was warmest. It was easy enough to chase out the pigeons during the observations. But they would coat the inside of the horn with their white, sticky dielectric material. Any substance like this would radiate and contribute to the measurement. Clearly, the pigeons had to go. When Penzias and Wilson dismantled their horn and cleaned it out, the signal went down a little bit, but most of it was still there. Evidently, its origin was cosmic. Now, the cosmos is very cold, about like this liquid helium used as a calibration reference during the measurements. But it seemed to them that even that temperature is surprisingly high. In 1965, Penzias told astronomer Bernie Burke of this problem during an informal telephone conversation. Now, Burke was aware of the prediction of the Princeton physicists, and he told Penzias, who then contacted Dickey at once. And it was thus that the scientific community learned that the dying glow of the primeval fireball had actually been observed. The discovery of Penzias and Wilson was the second great breakthrough in observational cosmology of our century. Their finding has now been rechecked many times over at many different wavelengths. In checking out ever finer details, observational cosmologists have shown remarkable ingenuity in selecting what sometimes must appear as the most unlikely equipment. One of these, a converted U-2 plane. These aircraft were flying regularly over the western United States as part of NASA's study of Earth resources. At the suggestion of University of California scientists, NASA Ames Research Center at Moffett Field, California, made available one of these valuable aircraft to study these microwave wavelengths, difficult to observe with conventional radio telescopes. Now it happens that the radiation is at its most intense at a wavelength where the atmosphere is pretty opaque. So we need to have observations above as much of the air as possible. For example, in a balloon or in a high-flying reconnaissance aircraft. University of California physicist George Smoot and his associates have placed these horn antennas right behind the cockpit. In principle, they're very similar to the ones that Wilkinson at Princeton has been setting up in balloons. They're very sensitive, and they have the advantage that they can look in different directions in the sky. And this gives us the opportunity to learn something about the uniformity of the microwave background radiation. That in turn tells us something about the structure of the early universe, much as the study of the distribution of rich clusters of galaxies tells us about the structure of the present universe. To the accuracy of all modern observations, that microwave background has the characteristics expected for radiation emitted by an early universe in the form of a hot gas. Of course, a gas that's long since cooled and condensed into galaxies and stars and us. We can calculate the conditions that we would expect for the early universe even during its first few seconds. But before then, science does reach a limit. As Lemaitre put it, it is the very first instant at the bottom of space-time. The today for which there is no yesterday. For yesterday, there was no space. Most modern cosmologists now believe that Lemaitre's general ideas about the explosive origin of the universe have been confirmed, and that the microwave background is indeed the dying glow of the blast that began the expansion of the universe. I think life was kind to Lemaitre because he lived to learn of this discovery of his vanished brilliance.